All right, the next couple videos are very, very cool, and the cats already know it's very cool. They're coming up real close. They're ready to learn some mathematics. The dogs are getting excited as well. It's going to be a fun time talking about, okay, said geometrically what's going on with straight line solutions. This just means straight line solutions. It's not a common abbreviation. I'm just kind of lazy and don't want to write it all out every time. So how can we do this algebraically? So let's look again at straight line solutions. So again, here is kind of our picture. We had a straight line solution. Everything along this line was a solution that stayed on this line. Everything along this line was a solution that stayed on this line. Again, moving according to the appropriate direction field, or appropriate direction vector on the direction field. So what we notice about straight line solutions is that at any point on that line, you must either be pointing directly towards the origin or directly away from the origin. Why is that? Because the origin is always in equilibrium of these systems, right? If we're looking at the differential equation dy dt equals a times y, and a is some coefficient matrix, it only has coefficients, then yeah, if y is the zero vector, the slope is also the zero vector. And that y, 0, 0 is always in equilibrium of these types of systems. So then, again, these straight lines are always going to go through 0, 0, which means that we must always be going directly towards 0, 0 or directly away from 0, 0. You can see along this line, oh wait, it's not showing my cursor. You can see along this line that we're going directly towards the origin. You can see along this line, we're going directly away from the origin. So let's write that down. Along straight line solutions, we must be moving directly towards or away the origin. That's going to be very important. Why? Well, let's write that down in math. Let's look at a point, maybe x comma y. Okay. So let's say we're at some point x comma y on some straight line solution. Then the direction that we're moving, that's dy dt. This is the direction that we're moving. Right? This is the vector that creates the vector field. And again, direction field is just a vector field with arrows all the same length. This is the direction we're moving. And I said the direction we're moving must be directly towards or away from the origin. So the direction we're moving must be directly towards or away from the origin. How do we write that? Well, if we're at some arbitrary point, x comma y, that means that the direction we're moving either needs to be it needs to be some constant, some multiple of this vector, right? Right? If we're some multiple of this vector, we're moving away from the origin. And again, if it's a negative multiple of this vector, then we're moving directly towards the origin. What is this vector? This is the vector x comma y. And the vector x comma y is denoted here, right? Y is x comma y. And again, this works for any multiple. Let's use the Greek letter lambda to say, okay, we can scale this green vector as much as we want, right? It just means it has to move in this direction, right? The direction directly towards or direction away from the origin. It's going to look like this vector, can be scaled positive or negative. And specifically, right, if lambda is positive, what's happening? If lambda is positive, we're going away from the origin. Right? So the vector field points away. This is going to be very useful for us. And if lambda is negative, well, what happens? The vector field points towards the origin. So this is a lot. And this is honestly one of the most important equations of linear algebra. Which again, linear algebra is not a prerequisite for this course. If you've taken linear algebra, you know exactly what you're looking at right here. And if you haven't, that's fine. We're going to spend 2 more videos talking about it. All right. So again, we've said something monumental, and I really want to recap what we've done. We said if we have a straight line solution, there's not always straight line solutions, but usually there will be for us. Well, at least in these sections. We talk more about other things in 3.4. So if there are straight line solutions, then at any point on that straight line solution, the vector field must point directly away or directly towards the origin. The direction that the vector field, remember the vector field just comes from this. The vector field is just dy dt, right? Y is just the xy vector. How the xy vector is changing, that's where those arrows come from in our direction field. Okay, that direction is ay. The direction must equal some constant of that vector. Okay, so let's play with this. Let's find those. We can find these no problem. Let's just take this equation and work with it. All right, what was a? Well, let's work with our last example where a is 2, 3, 0, negative 4. Okay, let's find lambda. Let's find the scaling and the direction. Let's call the direction v. Okay. So the direction that will put us on here. And again, I actually did want to call these v as well. So let's call this the vector v. Because it's not going to be true, right? We don't have straight lines everywhere. There's only specific vectors that'll make this true. Okay. So how are we going to do that? Well, let's write out what we have. So v is going to be some specific xy pair that we don't know yet. I mean, we do. For this example, we do, right? We do know the directions that these vectors are going to be going, but let's pretend we didn't. We're going to find a lambda and a v that make this true. And to do that, what is a? A was 2, 3, 0, negative 4. What was v? V, I said, was some ordered pair. And we want to find what lambda and v have to be so that a times v equals lambda times v. Well, let's simplify, right? This is just a times v equals lambda times v. Let's solve. This is a system of equations. This is just 2x1 plus 3y1 equals lambda x1. And then negative 4y1 equals lambda y1. And what do we know about the systems of equations? There are 3 unknowns and 2 equations. We know we're going to have infinitely many solutions. But let's also remember something about this differential equation. Something that we said in 3.1 about differential equations. We said that systems of equations, we actually said this is more a linear algebra topic, but we said that a times y equals 0. What did we say? We said something about singular matrices, right? We said it only has non-trivial solutions. If the determinant of a was equal to 0. So why does that help us? Let's move things around. Let's rewrite this system in this form. because we only want interesting solutions here. Of course, if everything is 0, this system is satisfied, but that's kind of boring. So let's move things around, and we're going to get 2x1 minus lambda x1 plus 3y1 equals 0, and negative 4y1 minus lambda y1 equals 0. Let's write this in matrix form. 2 minus lambda times 3 times our vector needs to equal the 0 vector. And the bottom one is 0 and then negative 4 minus lambda. I just translated this matrix form, this system of equations into vector form and matrix form. All right, this is the coefficient of x1, coefficient of y1. Coefficient of x1, coefficient of y1. We factored out the y1. We factored out the x1. And we get this. And we want non-trivial solutions to this. We're going to use this fact from 3.1. I know this is a lot. Stick with me. All right. So we're going to get non-trivial solutions if the determinant of this matrix equals 0. So what is that, the determinant of that matrix? Let's call this something. We have a very special name for this matrix. Well, let's leave it blank for now. Let's not worry about the name. Or we could just call it, what's your favorite capital letter? Z? No, that's a terrible one. How about we call it X? It's not great. But sure, we'll have a special name for it later. Well, we want non-trivial solutions because trivial solutions are boring. That's why they're called trivial. So what is the determinant of this matrix? We remember the determinant of a matrix A, B, C, D was just A times D minus B times C. You remember taking determinants. So the determinant of this matrix is going to be 2 minus lambda times negative 4 minus lambda minus, oh, thank goodness, 0 times 3. We need that to equal 0. It's really nice that this is 0 because it's already factored. If this wasn't 0, we'd have to combine like terms, FOIL out, and factor again to solve this equation. Because here's where things get really exciting. If you're not already excited, here's where things get really exciting. What values of lambda make this true? Lambda equaling 2 and lambda equaling negative 4. And I claim you've seen these numbers before. What are we doing? Let's put this all in perspective. Where are we? We're trying to find I almost said the word. We haven't mentioned what these are yet. We're trying to find lambda and this vector so that the matrix times the vector equals the constant times the vector. We're doing that so we can find straight line solutions. Because we said along straight line solutions, we must be moving directly toward or directly away from the origin. That happens when this is the case, because this is the direction that we're moving according to our differential equation. And this is what it would look like to be going directly toward or directly away from the origin. We're saying what constants will do that and what vectors will do that. And we found that the constant that does that is 2 and negative 4. Do you see any 2's and negative 4's here? Is it a coincidence? I don't know. We'll find out. How exciting, right? It's about to get a heck of a lot more exciting. So these are the lambda that are going to do that. We still need to find out what vectors will do that. Okay, so we're kind of running out of space here. But we want to know, right, what vectors will go with these lambda? So we'll plug it in. we'll go back to this, right? This is what our mission is right now. So if lambda equals, let's pick one. Let's pick one to start. If lambda equals 2, we'll do something. And if lambda equals -4, we'll do something else. So if lambda equals 2, what happens? We get 2x1 plus 3y1 equals, if lambda equals 2, we get 2x1. The 0, this just becomes -4y1, needs to equal 2y1. All right, if lambda equals 2, this is what we have. And notice something very interesting. See? The 2x1s cancel. These are redundant equations, and it's kind of hard to see that they're redundant equations, but look at what these equations become. These equations become 3y1 equals 0, and if we subtract 2y, we get -6y1 equals 0, right? These are redundant, and they always will be. Why? Why are they redundant? Because we're looking for a vector that makes this true. Well, remember, this green vector would have worked, but also this blue vector that's bigger would have worked. It's any vector that's in the same direction will work. There are going to be infinitely many vectors that do this. Right? Because if we have one vector that does this, if we double the vector, that's just like multiplying both sides of the equation by 2. So it's still going to work. All right. So there's infinitely many vectors that work. All we know is that for a vector to work, for lambda equaling 2, we know the y component has to be 0. And the x component can actually be anything. We can choose any vector, any of these will work. You know what I'm going to choose? My favorite number in the world. I'm going to choose the vector 1, 0. Let's choose x to be 1 and y has to be 0. So that's a vector that goes with this lambda. And you know what? Let's call this our first lambda. Let's call this our second lambda. And this is our first vector that goes with that first lambda. Does this vector look familiar? Maybe, maybe not. Let's find out what vector goes with the second lambda. Well, we're going to do the same thing. Try to model what we did here. Pause the video. Try to see if you can model this process to find what our second vector has to be. We'll get plenty of practice with this, but now's a good time to do it. So we plug that in again. The left-hand side is going to be the same. We still need to, let's call it x2 now. You don't have to, but let's do that. Plus 3y2 needs to equal now -4 x2. And then again, -4 y2 needs to equal -4 y2. Oh, interesting. Why is this interesting? All right, the left-hand side's the same. I just changed them to 2's as a subscript. You didn't have to. And then the right-hand side, right, the coefficient changes. Lambda's different now. Well, this second equation is always satisfied. And remember, I said these need to always be redundant. You can't read that. It says redundant. All right, so we really just need something that's going to satisfy this first thing. What is this first thing? This first thing says 6x2 plus 3y2 needs to equal 0. That's the equation of a line. What line do you think this is? Do you think possibly it could be the equation of this line? I don't know. Let's find out. What line is this? This is the line, subtract the 6y2 over, or sorry, subtract the 6x2 over, divide everything by 2. That's this line. The line y equals negative 2x. Is that the line y equals negative 2x? You bet it is. What a crazy coincidence. And again, any such x and y will work. They just need to follow this. So, you know, you could choose whatever you want. I like choosing nice numbers. I might let x be 1. And if x is 1, the y has to be negative 2. If you wanted to be really consistent with what we had earlier, you could choose x to be negative 1, y would be positive 2. So, we said we're looking for lambda and v. That is going to help us find our straight line solutions, because that's when we're moving either directly towards or directly away from the origin, which translates to solving this equation. We found that happened for 2 values of lambda. For each value of lambda, we found infinitely many vectors, all with the same direction, infinitely many vectors that satisfied that. So, we just found our straight line solutions. And it all came back to this extremely important equation, which is fundamental in linear algebra, which you can take in a future quarter if you haven't already. Okay, so this is pretty exciting, because yes, these are the vectors that correspond to these lines for this system. Furthermore, again, we can multiply this by any constant we wanted. Let's multiply this by the constant of negative 1. Right? Anything that satisfies this equation is going to work. Look at what we have right here. Look at these vectors. Look at those lambdas. Look at our solution. We had one solution with this lambda and that vector. Solution with this lambda and that vector. Is that a coincidence? No. And in fact, in the 6th video of the section, we'll talk about how to come up with the general solution. But in the meantime, just think about what the general solution might look like to an equation like this. It'll have to combine things like these vectors and these values. We have specific names for these vectors and these values. We introduce those in the next video. It'll have to do with linear independence and how you can, remember, if you have 2 vectors that are linearly independent, then you can create any other vector with some linear combination of those vectors. Oh my gosh, it's so much fun. I can't stop talking about it, but I need to because I've talked long enough in this video. All right, so that is it for this video. That's our solution here. We just did a ton of linear algebra. The last thing I want to say, right, is remember that this means we're going away from the origin because it was a positive scaling. This means we're going towards the origin. That was a negative scaling. We'll see that along this vector we were going away from the origin. Along this vector we were going towards the origin. That's a big important point. But we'll talk more about this in the next video. The next video talks and unpacks a little bit of the linear algebra we did. Anyway, it's very fun. Very fun, but I gotta cut myself off. Thanks for watching. See you in the next video.